Hi, Dr. Revis here with Watch Me Work It, determining isoelectronic species by math, periodic table counting, and electronic configuration. Watch me work it. Let's work a problem. What neutral element is isoelectronic with the following ion? I'm going to pick an ion and then I'm going to show you how to determine what's isoelectronic with it. I'm going to pick carbon with a +4. We know that carbon is atomic number 6, so it has originally 6 total electrons, and now we've oxidized it to +4. When we do oxidation, we remove electrons. So mathematically, we would take our math approach to this, would be 6 electrons, minus the 4 electrons due to oxidation, and we end with 2 electrons. So we now look throughout the periodic table and see what has 2 electrons, and there it is. Helium has 2 electrons. So that means carbon +4 is isoelectronic with helium. Okay? They're not the same because the number of protons are different, but the electrons in the species are the same, which means their electronic configuration is the same. Well, let's check this another way by simple counting on the periodic table. Here's how we count a periodic table. Start at the element of the ion. So we have carbon here, and we count backward for oxidation to the left, 4 blocks or 4 spaces back. 1, 2, 3, 4. That means we're basically removing 1, 2, 3, 4 electrons. We land at helium. So if I do counting on the periodic table, I just count backward, count left, 4 spaces, 2 helium. Now, if I check this by electronic configuration, let's write it for carbon. We have, I'm just write the original carbon first. 1s2, 2s2, 2p, only 2 of these. That's 4 valence electrons. I see them. I see my 4 valence electrons right here. That's good. So now carbon +4, what would happen in carbon +4 is, I'm going to write the original again, and then I'm going to remove those 4 electrons. 2 electrons gone. 2 more gone. I'm left with 2. And if I write the electronic configuration of helium, it's 1s2, a match. So, carbon +4 is isoelectronic with helium. It is not the same as helium because helium has 2 valence protons, and carbon has 6 protons. Okay. Let's do one more. Let's do phosphorus -2. Phosphorus doesn't like to be a -2, by the way, but I'm forcing it to do that for educational purposes, so I can teach this lesson. All right? So here we go. Phosphorus -2. So I take phosphorus -2. Originally, phosphorus has 15 total electrons. So this is reduction. So the math for reduction is the original electron count, and we're going to add electrons because reduction adds electrons, and now we get 17 electrons. So then I look throughout the periodic table for 17 electrons, and there it is at chlorine. So chlorine, atomic number 17, is isoelectronic with phosphorus -2, which is atomic number 15. They are not the same because the protons are different. Okay, I can do this by counting on the periodic table. So periodic table count, move right. How many spaces? You guessed it. 2 spaces right. 1, 2. Get it again? Start at phosphorus. 1, 2. That's -1, -2. By the way, -3 is the most popular one. We'll put us at argon. So let's finish this one. So we count 2 to the right, count right 2 spaces, and we land at chlorine. If we write the electronic configuration, we can tell this too. Let's write phosphorus. First, phosphorus 15. Let me clean it up just a little bit for you here. Okay. So phosphorus 15. And so we would have a 1s2, 2s2, 2p6. And now we're on the quantum number 3, 3s2. And now we'll move to the p and we count over 1, 2, 3, 3p, 3, 5 valence electrons. I see them. I see them right here. The highest potential quantum number. I feel good about that. So in order to do phosphorus -2, I'm going to rewrite this. And then I'm going to remove 2 electrons. And I'll have a, no, I'm going to add 2 electrons. I have 3, 4, now I have a 5. So I'm going to add 2 electrons. Okay, so when I add those 2 electrons, that electronic configuration looks just like chlorine. 1s2, 2s2, 2p6, 3s2, 3p5. Okay, and that's how we do isoelectronic species. Now, just for the fun of it, let's do one more that's a little bit more bizarre, that challenges you a little bit more. Let's do one that you really don't want to see, but I'm going to make it do oxygen -4. Can you believe it? Yeah, oxygen -4. I can't believe it either, but I'm going to make it be an oxygen -4. We know oxygen starts with 8. That's its atomic number. Okay, we see it right here. And so by math, we have 8 plus 4 is 12 electrons, because this is reduction. So I look throughout the periodic table for what has 12 electrons, and it's right here at magnesium. I could check it by count. So I would count 4, right? And I find myself at magnesium. 1, 2, 3, 4. Do it again. Oxygen. 1, 2, 3, 4. So that works out really well. So we believe that this is isoelectronic. Oxygen -4, which is really hard to do. It's isoelectronic with magnesium. We can also check the electronic configuration. We have oxygen, 1s2, 2s2, and 2p, 1, 2, 3, 4. P4, 1, 2, 3, 4. That looks right, 8 electrons. So if we do oxygen -4, it's 1s2, 2s2, 2p. We have to add 4, but p maxes out. We know we have s max 2, p max 6, d max 10. So we're going to max this out at 6, and that means we're now in principal quantum number 3, 3s2, which is the same as writing magnesium electronic configuration. And there you have it. So that's how we do these isoelectronic configurations and identify the element that is isoelectronic with. All right.